Just a quick introduction here. Brad Thoen, he's been with MTS, I don't know, 38 years?
40 years
40
January.
40 years. And I've had the great pleasure to work with Brad on many projects, including this project. Brad, he has been our controls theory gentleman for a long time, developing most of our seismic table and 6 degree of freedom software and a lot of our models for actuator and model systems for our hybrid systems. So, you know, Brad goes back a long way, and when we worked on all of these niche projects back in the 2000s, Brad was instrumental in helping deliver the concepts and the message to things that MTS could do that would help all of our customers, you know, actually build the things that they envisioned for NSF. So really, Brad, I can't thank you enough for all the work you've done for the hybrid systems and for seismic testing over the years, and I'll let you talk all about degree of freedom control.
Okay. All right, today I'm going to talk about seismic system control. And a seismic system has a lot of similarities with the MAS system here, with some important differences. The MAS system is, of course, very, very slow, whereas the seismic system is very, very fast. And the control features in the seismic controller have to reflect that. Another difference is that this MAS system not only can it do motion control, namely displacement control, but also force control, whereas a seismic system controller only supports motion control, displacement, velocity, acceleration. MTS has some very sophisticated motion control technology used in a variety of applications, driving simulators, wave makers, and of course, seismic shake tables. This kind of shows the topology of a seismic controller, but also this does apply to the MAS system here to some extent. We do control in degree of freedom space. We do not control actuators directly. Some advantages to that. So we see here in a 6 degree of freedom system, we'll have a controller for X, Y, Z, roll, pitch, and yaw. And these controllers get their feedback from the table sensors through a coordinate transformation that transforms them from actuator space to degree of freedom space. The degree of freedom controller outputs are all assembled together and have to be converted back into actuator commands, servo valve commands, and that's done with a Jacobian matrix. There's some other things in here that are, well, so far I've pretty much described the MAS system, but seismic controllers need to have something extra because of the dynamic nature of it. The motion controllers, although they do a good job of controlling, they don't do a perfect job. And so often that needs to be augmented with adaptive controllers that are an outer loop around the motion controllers. Another thing here is force balance control. By the way, that is here on the MAS system. Anytime you have more actuators than degrees of freedom, you have to provide some more constraints. And this system here is 8 actuators with 6 degrees of freedom. So the force balance controllers provide those extra constraints so that the forces just don't wander around. And I'm going to talk more about that in a little bit. Last thing that looks like it's cut off, kind of a new thing here is in seismic control is a thing called specimen dynamics compensation. And this will compensate for a specimen that's pushing back on the table quite a bit, and therefore making the response less than ideal. Our basic motion controller is this thing we call 3-variable control, TVC. And what that is state variable control plus extras. State variable control is the most generic control topology there is, and if you ever take a course at your university, that's all they're going to be talking about is state variable control. And with state variable control, we take the command signal, that's called reference in seismic land, and we develop its states by differentiation and integration. So we have displacement, velocity, acceleration, and jerk. We also do the same thing with the feedbacks, develop their states, and then by combining these states, both reference and feedback states, with these gain elements, you can achieve any control goal that you want. So there's an extra thing here, other than state variable controls, this thing called stability gain. This is really, really important in servo hydraulic systems because the natural frequency of the oil column with that huge mass of the table and specimen is often, that frequency is often very, very low and very low damping, usually like 5 or 6%. It has to be, the damping of that mode has to be increased, otherwise you won't get good control. So the thing that does that is this stability gain here, which takes the force feedback that the actuators are providing and just blends that in to the regular controller output. And it works like magic. There's some other things here. I won't go into too much detail, but we also put these things here called notch compensators, which I'll be talking about in a little bit. Okay, TVC tuning. I should go back here. You see these gains right here that work on the reference signal, states of the reference signal. These are called feed-forward gains. They're not in the feedback loop. They're just they only operate on the command signal. And those are very useful for getting bandwidth because if you did not have those, if you just had to rely on feedback signals, this would be the most bandwidth you get out of the system is this dotted line here, and where this is the oil column natural frequency. Whereas if you put a little bit of feed forward in there, you can get often 3 to 4 times the oil column bandwidth just with feed forward. So it's a really important set of gains in a seismic controller. We make a lot of use of them. Okay, notch compensation. All right, everyone thinks of a notch filter as something that is very narrow bandwidth, and what it does at a certain frequency, it removes all frequency content and then goes back to unity gain. And that is the classic notch filter. But a notch compensator is one that's more general than that. The notch doesn't have to go to 0. It can go down any distance you want to go. And in fact, it doesn't have to go down. It could go up like this. And what this notch compensator is useful for is to compensate for resonances and anti-resonances in your frequency response. As seen in this diagram here, do you see this dotted blue line? That's a system that has a very heavy 5 hertz, 5% damping specimen on it. And you can see it makes the frequency response very non-flat. If you can take a notch compensator and make one that goes down here, you can compensate for this upward rise in the frequency response. And likewise, where you have this hole in the response, you can go the opposite direction and build up that response. And overall, you get this, this red frequency response. So it's really good for resonances and anti-resonances. All right, well, these are a lot of things to tune, and most people have no idea. Most customers are afraid of these controllers. They don't want to touch them. They don't want anything to do with them. And even our MTS expert tuners will spend a lot of time tuning a system. So what we've recently developed is an auto tuner. It shows the main panel of it. It's an application that connects into the controller and excites the system, measures frequency responses, optimizes all the gains, does that for each degree of freedom, validates all those gains. And with this application, you can tune a 6 degree of freedom system in 20 minutes tops. So it's quite the feature. It's a nice new feature. Here shows the results here of the red is what the auto tuner thought that it would get for a final response, and then we sent those to the controller and then measured the actual response in blue. You can see here they're very close, and notice it's extremely close to unity. So very good to get a flat response. So the auto tuner does the TVC tuning, but there's another thing that needs to be tuned in the system, and those are servo valves. We often in seismic have 3-stage servo valves, and the third stage needs to be tuned because it's a control loop. It has proportional and derivative gain elements in it, and it often takes a lot of time because often there's many, many servo valves in the system. And this shows the results here of what the tuning was with default tuning, basically untuned response. And then after the auto tuner got done, it's nice and flat and out to a large bandwidth. So it takes about 10 seconds for it to do that. All right, so now I'm going to talk about degree of freedom control, which totally applies to this mass system here. Okay. Before I talk about degree of freedom control, let's talk about the way people usually implement degree of freedom capability. Often they keep the actuators in direct actuator control. In other words, there's a controller for every actuator, and it looks at the command and looks at the actuator feedback. And the way that they make it appear as though it's a degree of freedom system is they'll have a coordinate transformation that computes the actuator commands based on degree of freedom command. And then to read the results back in, the feedbacks, and they often like to see them in DOF space. So they have another coordinate transform that will act on the actuator feedbacks to come up with degree of freedom feedbacks for monitoring purposes. That's the usual way a lot of people do this. Most natural way, I guess. But we don't do it that way. What we do is we have a controller for every degree of freedom. It works on the degree of freedom command directly. It gets degree of freedom feedbacks after a coordinate transformation. And then when the degree of freedom controllers come up with their control updates, it's converted back into servo valve commands via a Jacobian matrix, which is nothing other than an approximate transformation from DOF to actuator states. And this has really big benefits. One is that it orthogonalizes the rigid body modes of the system. Remember I was telling you that when we looked at the TVC panel that talk about oil column resonance. Okay, very, very significant, very low frequency in most seismic systems, has to be dealt with. It's very low damping. Well, that is a rigid body mode, and you have one of those for every DOF. Okay, if you were in actuator space, all those rigid body modes would be intermingled into one, and you wouldn't be able to have a single tuning gain that would apply to just that particular mode. But if you orthogonalize the system by the use of coordinate transforms and control in DOF space, one little adjustment there, that one I showed you in the TVC panel, will completely suppress a rigid body mode. And you've got one of those for every degree of freedom. So it really makes tuning possible. All right, another feature of this mass system, as well as all seismic systems, is if there are more actuators and degrees of freedom, you got to do something because you don't have enough constraints on the system. So you're going to need a thing called force balance control, which I'll describe here now. Okay, the upper part of this diagram here in the dotted line here is the motion control part of the controller. And it's basically a different drawing of the one I showed you before at the beginning of the talk. But what it does is it causes motion to occur, but in order to get that motion, you require a certain force, certain degree of freedom force in moments, okay? So in other words, the motion controller is basically asking the system for a certain amount of force, okay, in order to do its motion thing. But the trouble is, if you don't have force balances, there's an infinite number of actuator forces that will deliver those degree of freedom forces in moments, an infinite number. And in fact, they could go all over the place. They could drift everywhere. And here's an example where we have a case where there's like 3 actuators in the X direction. And we want to get a certain Fx out of here in order to support a certain motion. They could be doing something like this. You'll have one that's pushing a lot, one that's kind of pushing a little, and another one that might even be pulling, retarding motion. Well, anything's possible if you don't have the constraints. So what we want is we want all the actuators to push and pull together. So the way we do that in the force balance controller is, first of all, we have to find out what force the motion controller is asking for. So we go to, we convert the actuator forces to DOF forces. Then we take that and we go through this optimum actuator force distributor, which is kind of our IP. So it's kind of a funny name. But what it does is it takes that desired degree of freedom force and computes optimum force commands that are as close to each other and as small in a least square sense as possible. So what's going to come out of there is commands that will say, okay, in order to get this degree of freedom force, you need each actuator to be equally pushing. Now we need to enforce that, because that comes out as a command. So what we do is we put a controller, a servo controller on each actuator, which takes the optimum force command and the actual force feedback and comes up with a control update that gets added to the servo valve command. So that is how it forces the system to get those. They shouldn't use the word force, but it causes the forces to gravitate into a situation where they're all working together instead of fighting each other. Okay, now I'm going to move to adaptive control. All the adaptive controllers in our seismic control product are an instance of inverse control. And the basic idea is, okay, you've got a system here you want to control. It has a frequency response T of omega. What you want to do is you want to measure online adaptively what that inverse is, or what the inverse of that plant is, or what T inverse is. And you use that as a precompensator to your command so that the overall response is one for all frequency. That's the basic idea of all inverse control. So we have 5 different adaptive controllers, depending on what you're trying to do. They depend on what type of waveform you're trying to reproduce and then what your expected system linearity is. If your programs are sinusoidal or sweep or sine step or just something sinusoidal-like, and your system is mainly linear, we use this thing called amplitude phase control. It does a beautiful job. If you have significant nonlinearities, you're going to get harmonics generated, and you can cancel those with this thing called adaptive harmonic cancellation. Anything non-sinusoidal with linear dynamics, AIC, adaptive inverse control, is the thing to use. And if you have nonlinearities, this thing called online iteration, or this product that we make that's a separate application, STEX, you can use that. We have a new one here, adaptive feed-forward compensation, that was mentioned in some of the other talks. This is the algorithm by Dr. Che of Lehigh University as adapted by MTS in order to make it extremely efficient. And it works with either program shape. So it's kind of in a different category. All right, looking at amplitude phase control, this is the basic idea here. You take the command and you run it through this network right here, okay? What you do is, let's say you had sine omega t, create cosine omega t, and then you weight those two with the 2 gain factors, and by adjusting A and B, you can come up with an output that is any amplitude and any phase. So what the adaptive controller does is it figures out what A and B should be such that the amplitude is T inverse, the system, which is measuring continually, and so that the phase is minus the phase through the system. And this shows an example of it working. Here's a command and response before APC is turned on, and then when APC is turned on. And it adapts very quickly within seconds. All right, so now the case you're doing sine wave programs, and now you have some bad nonlinearities, you could get a lot of harmonics, okay? The harmonic canceller, what it does is it, in a nutshell here, I won't go over the details, but what it does, the idea here is you've got some harmonics here you want to get rid of. One way to get rid of them is put in a sine wave of that frequency, that harmonic frequency, with just the right amplitude and just the right phase so that when it goes through the whole system here, it comes out here and cancels it. So it's basically it's like noise canceling headsets like for helicopters. In fact, that's the same algorithm we're using in here. Here shows some examples. Here's command and feedback with AHC off. You see the harmonic here at the third harmonic. Other ones in there too. In the frequency domain, if we plot it, that's the fundamental, which we want. And here are all the harmonics on the feedback, odd harmonics. When we turn on AHC, in the time domain, it cleans up really nicely. In the frequency domain, the fundamental is there, but all the harmonics are gone. All right, so now, what if you had a non-sinusoidal program? Then you'd want, in a linear system, you want to use adaptive inverse control. And it's kind of like APC, only it works at all frequencies. So I won't go into the detail here about how it works. But here's an example. Here's command and response with AIC turned off. And then with AIC turned on, you get much better following. In the frequency domain, this with AIC turned off, we had this blue response here, which is caused by our heavy resonance specimen, a resonance anti-resonance. And what AIC did is it developed the inverse of that, as you can see here, so that when AIC is turned on, your frequency response is unity over all frequency. AIC is capable of handling cross-coupling. In a seismic system, you've got lots of cross-coupling, especially linear into rotation. AIC will figure out the inverse frequency response, but it's not an element inverse, it's a matrix inverse. So in this 2x2 example here, it shows that the inverse created by AIC, when it's coupled with the system, will develop 1 on the diagonals and 0 on the off diagonal. So it basically cancels cross-coupling. Here's an example. Okay, this is looking at longitudinal to pitch acceleration disturbance. Without AIC turned on is this blue here. And when you turn on AIC, it goes down to this low-level green. In the frequency domain, the blue waveform here is with AIC turned off, and the green is with AIC turned on. So you can often get, 10, 20, 40 dB of cross-coupling rejection with AIC. Okay, now what if you have a non-sinusoidal program and you have a lot of nonlinearities? You have to do this thing called iteration. And with iteration, it's exactly the way it says. It says you play out this waveform and hope for the best. And you measure how it responds versus what you want, develop an error signal, and then you modify your excitation signal accordingly so that when you play it out again, it's that much closer. And you just do that again and again and again, iterate until you get good response. So simple as that. Here's an example of El Centro here, desired versus achieved. You can see here without OLI, we have a lot of mismatch, especially after the big event. And then with OLI, after a certain number of iterations, you get really good following. That you can't even tell it's two FRFs there. Okay, this is the 5th adaptive controller. It just came online this year. This is based on Dr. Che's algorithm for reducing delay. He calls it adaptive time series compensation. that wasn't a descriptive enough title for me, so I call it adaptive feed-forward compensation. And basically what it does is it takes the states of the command signal and then applies a gain to each one and does that adaptively so that you get good response. So you can kind of think of this as, remember I was talking about the feed-forward terms of TVC? Think of these as the feed-forward terms of AIC, or of a TVC, only they're adaptive. In fact, I actually use AFC to auto-tune those gains, the feature in our controller where you can say, you don't want to figure it out, let this guy figure it out. So. All right, here's an example of AFC off. You can see a lot of delay here. You see some mismatch in the response, the amplitude here. And then with AFC turned on, the response is a lot better, but notice it's a lot less delay. And if we look at the delay response here, we started out with 40 milliseconds of delay, and with AFC, it went down pretty almost zero. Just a millisecond or two in there. So AFC does do what Dr. Che intended, which is he intended it mainly as a delay reduction algorithm when you're doing hybrid control. But it's also good for doing not just delay reduction, but also fixing up the frequency response, the magnitude response. All right. Here's something that we developed. Actually, this is from 1983. We had a patent on this technique. And it languished for about 20 years, and then about 8 years ago, I picked it up and tried to figure out why it languished and found out there was a lot of things that needed to be done to it, a lot of detail work. And we've resurrected it, and it really does a good job in a seismic system where the specimen really pushes back on the table. But when you have a heavy resonant specimen, it can push back on the table so much that you don't even get the table, it can actually stop the table. You get zero response at that frequency. So the idea here is figure out what that reaction force is, figure out what the specimen is putting back into the table, and then tell the actuator to provide just that much more force into what it's already providing. So what we do here is we measure the specimen reaction force, and we usually do that with the table sensors. It doesn't require any additional instrumentation or hardware. So we take that reaction force, we run through an inverse model of an actuator, feed it into the valve command, then it goes through the actuator again. So you got K inverse times K times Fs. Well, that's Fs. So the specimen force comes out here. It's been augmented by that amount, and therefore cancels what the specimen is putting into the table. Really simple in concept, but it's devilish in the details, I'll tell you. Been at it for years. This shows some examples, real examples from field tests. We had a system here with a really low frequency resonance, and you know this resonance was changing as we were doing the testing because we had this, what do you call it, a welded fuse where the welds are just breaking as we were continued running. And that frequency is shifting down, but we never saw it in the FRFs that we're looking at because this algorithm will track a nonlinear and changing specimen. It doesn't care what gave rise to that specimen force, that reaction force. It doesn't care what the dynamics are. There's no modeling of it, nothing. It just says, take this and cancel it. And so so this resonance you see here was actually, I think it started out around 5, and when we measured it here, it was around a little over 3. And you can see here how the magnitude response with SDC on really cleaned up. This is the phase response. You can see a big hole here caused by that resonance, and then it flattens it out. And here's a nice thing is even the coherence was improved. Coherence was quite low until we turned on SDC, and then it went right back up to unity, which is what you want. All right. This is a feature that we have in all of our seismic controllers. Now it's called damped abort or safety stop. Now, if there's a limit or something in your specimen in your system, you want to bring the amplitude down of your command waveform. And the way that we've done that for many, many years is we have a multiplier on the output of the function generator that's developing our command. And it just simply ramps to 0, and we multiply that by the output of the function generator. Okay? So normally it's this blue waveform right here, where we would just ramp that down, and so the amplitude of the sine wave would go down, or whatever waveform you're running. Well, you could do a lot of damage there, because while it's coming down, you're really shaking the table. So we have a thing here that what it will do is not use that approach. What it will do is it'll, when you want to stop, it measures the state of the command, displacement, velocity, and acceleration and jerk, and then in a damped way brings all those 4 states down to 0. Smooth, relatively quick way, but you can specify how quick. But you can see here you get to 0 a lot more quickly, and it's a lot less hard on the specimen. I've had customers call me up and say, "Brad, your safety stop saved my specimen today." You know? So it really works well. Okay, this is a feature of all of our seismic controllers, and also this system right here is the ability to simulate the controller non-real time, to actually use the actual control software, not a simulation of the software, but the actual control software. But instead of running the real system, it can run a simulate model of the system. It has a little animation with it here, and so you can use this for like doing performance prediction or control fidelity studies. You can use it for training. That's what I use it for when I give my classes. You can use it for offline tuning, because you can shake this system all you want and nothing's going to get hurt. So if you want to do manual tuning, of course now with the auto tuner, the use of that is diminished in importance. So the way this works here is this controller application connects to Simulink via UDP, sends some valve commands over, clocks the Simulink model. Simulink model runs, and you get a set of feedbacks, and those feedbacks then go back into the controller application and back via UDP. And it just does that as fast as it can do it. And it's so fast that it almost feels like real time. In some cases, faster than real time. I won't go into this in great detail, but this is our forward model of a 6-degree of freedom system that we use in a lot of places. But our valve commands come in here, and then we have a block here which handles any number of actuators. You know, it could be 8, 12. Recently I did one with 46. And out of that comes actuator forces. And so we convert those actuator forces to degree of freedom forces at the origin of the table. We subtract from that various specimen reaction forces, and we take the net force and convert it up to the CG of the system. And here is, we do Newton's second law of motion, F equals ma. And we get the motion out at the CG. We convert that down to the origin, and then we convert it once again down to actuator feedbacks, like displacement feedback, force feedback, or accelerometer acceleration. So that's it for the modeling thing here. You guys have seen this slide here in another talk, but this shows that all of our controllers are meant to work with larger systems, multi-table systems, or with other types of devices, or with National Instruments data acquisition systems, or you know, XPC target boxes, or whatever you can dream up that is on ScramNet. So here, this is an actual system at University of Nevada, Reno. They've got 3 biaxial tables controlled by this guy here. They have a structural test system that's controlling these actuators here, this guy right here. They do all their data acquisition in National Instruments. They They have all sorts of National Instruments boxes here, and one of these is the compute engine that they have. Real-time, XPC target right here. They have a box from National Instruments for command generation. They want to get coordinated commands, so it's really nice for hooking these controllers into other systems. And if you guys don't know what ScramNet is, I think this is my last slide. What that is a distributed shared memory system. And what it does is if you have a whole bunch of different processors here, and you put one of these ScramNet cards in each one, what it does is it makes it look like there's a shared memory, a block of shared memory that everyone can see, no matter how separate these processors are. They can be in different buildings. And all one processor has to do to talk to another is simply drop a value in shared memory. And with ScramNet, which is a fiber optic link, it'll update all the copies of the memory in all of the machines that are connected to ScramNet. And it happens within, I don't know, a few tens of nanoseconds now. They've really got it speed up quite a bit. I won't go into that. It's controller features. And that's it.